Hello everyone, welcome to Rasayan Academy guys. So continuing the series of best questions on TIFR. So guys, I hope that you have already seen the previous videos. We have done few topics, pericyclic, stereochemistry and coordination, right? So also we are going to have more such topics of both the organic, inorganic as well as physical chemistry. So yes, if you haven't seen those, please do. These are all really important questions. And today we are going to do 10 important questions, very important and tricky questions of TIFR and under the topic organic reaction mechanism. More such topic discussion going to come up. Alright guys, so the first question we are starting back from TIFR 2010. Okay, so the question is rank the following molecules in the order of electrophilicity from most to least electrophilic. Alright. So what is electrophilic? Basically the one which is easily attacked by a nucleophile or the one which is most electron deficient. So all of these you can see are carbonyl compounds, and which one is going to be the most electron deficient depends on two factors, that is the electronegativity of the group which is attached next to the carbonyl other than the carbonyl, right, and the resonance, also the plus R effect as well as the minus I effect. Both of these factors contribute to the electrophilicity. Now let's consider this. First of all, as you can see that the acyl chloride is going to be most electron deficient because the plus R effect is very less as compared to the minus I effect of chlorine. That is why the carbonyl is going to be electron deficient, and that is why most electrophilic. So you can easily start from 2 is going to be the greatest. Okay, now who is going to be the least electrophilic? Option number 1, because the plus R effect of amine group is going to be much higher as compared to the minus I effect, right, and it is going to donate electrons to the carbonyl, and that's why this is going to be least electrophilic. So these two things you have already arranged about 1 and 2. Okay, what about the options? So 2 is the highest, 1 is the least. You have two such options like this. The rest are going to be wrong. So as you can see, A or C could be the right answer. But if you see guys about the comparison in 3 and 4, if you see that sulfur cannot donate the electrons because these electron pair are going to be there in the 3s orbital. However, oxygen, even though the minus I effect is greater because of greater electronegativity, but still the plus R effect is higher. Okay, so the plus R effect is going to be higher than the minus I effect. Same should have gone over here, but the resonance is poor. Resonance is poor over here. So this is going to be more electron deficient. So 2 is the most electron deficient, then comes 3, then comes 4, which is still doing some resonance, and finally comes 1. Alright, so this is your correct answer, option number A. So this was back from TIFR 2010. Moving on to next question. Question from TIFR 2015. Okay, now this is a tricky question. What would be the likely ratio of products X and Y for the following reaction on 2-methyl cyclohexanone if we consider that the torsional effects play a significant role in the reaction outcome? So basically guys, this is your cyclohexanone molecule, 2-methyl cyclohexanone molecule which is mentioned, alright, and if you are visualizing from this bond, if you look at this from this bond, you will see that the methyl is going to be on the top like this and the hydrogen is below. I hope that you can see from here, okay, on this line, right? So basically see, it's made easy for us. We just only have to say that where the hydride attack is taking place, the already the confirmation is given. So here the hydride attack, H minus attack, takes place from the side like this. Okay, that goes to X. Alright, it will be O minus. And in second reaction, the hydride attack is taking place from here. Okay, or rather we should write Burgee unit's trajectory is followed 107 degrees from the top. This is followed H minus, and Burgee unit's trajectory from over here from the bottom H minus over here. Torsional effects are those of the steric effects having an angle. So usually a carbonyl will be attacked on an angle of 107 degrees. You know that this is known as Burgee unit's trajectory, right? So this is known as Burgee unit's trajectory. Now it will be very easy for you to determine that which position is going to be more hindered, because you see that there is going to be a methylene group on both above and below. This is your carbonyl, carbonyl is below, right? So on this side there is a methylene group, on this side there is a methylene group. However, the hydrogen which is present below is making this attack hindered. And here there is nobody lying in between the Burgee unit's trajectory, 107-degree angle. So definitely the hydride is going to give the above attack. So this is going to be your major product. This is going to be your minor product. So 50-50 is never major and minor. 20 of X and 80 of Y is just the opposite. So it's going to be option number A, 80-20. X is major, Y is minor. D is also wrong. Okay, so this was the question. Very nice one. Now moving onwards to another question from TIFR 2015, that is asking you, thiols are important molecular species present in the cells and can mediate cell signaling processes. Okay, a procedure for detecting thiols has been recently reported based on the following reaction. Predict the structure of the reaction products. Okay, now this is at pH 7.6, which is your physiological pH, and this is doing a big reaction. A big molecule is reacting with a thiol basically. All right, now how the molecule is going to react with this thiol, that is the question. Now it's very simple. You just have to find the electrophilic center who is going to be attacked. Just have to find an electrophilic center who can be attacked by the thiol at the physiological pH. So either there could be this carbonyl which is attacked, or there could be this carbon which is attacked, or there could be the sulfur which is attacked. And let's see what makes sense. Okay, for example, your thiol over here has attacked this sulfur. What will result? The bonds could migrate in such a way so as to give you this kind of a fragmentation. What will that result into? That may result into option number A. There will be a new sulfur-sulfur bond. There will be a molecule like this, and the O minus, the negative charge is on the oxygen, which is going to take away the extra proton from the thiol to be protonated like this. That would be correct. Okay. So A option makes sense. Now look at option number B, C, and D. What is happening? In option number D, you still have the attack on the sulfur, but what happens is, yes, you still have this molecule, but the O minus, which was generated over here, O minus, this has attacked on the sulfurs. Now sulfur could be electrophilic group, but hydrogen is not a good leaving group, right? So option number D is as it is wrong. Okay, similarly option number B and C, you have to check that what is going on here. The sulfur has attacked on this carbon, on the second carbon which is connected to oxygen. Now oxygen is not a good leaving group as such, so that is why what will happen, you cannot directly get this product. Okay, and this will be a sterically hindered position to attack. So both of the option B and C, they are wrong because it is attacking on a sterically hindered position. Okay, so your answer is option number A. So moving on to another question. Now this is a very nice question, TIFR 2016. The question is asking you, predict the products of the following reaction. Now what are you supposed to do, guys? AgBF4, this is going to be your Ag positive, BF4 negative, and PHCl is just your chlorobenzene, which is the solvent. So this is the solvent. All right. Now what happens is, look at all of your options and also look at silver positive. Silver positive will usually, this usually takes away the halide, not the positive halogen cation. So it is there to remove the whole Cl minus along with Ag plus. If that happens, the Cl minus is removed, then you are going to have a positive charge like this. You are going to get a positive charge on the carbonyl, which in turns break down this bond to eliminate carbon dioxide and give you a forbidden bridgehead carbocation. Alright, so this reaction might not look like a feasible reaction because you are getting a positive charge over here on a bridgehead position. But what happens next is the solvent, which usually is not a good nucleophile. This is not a good nucleophilic solvent. But then this solvent also, it can attack on the carbocation because the carbocation is highly unstable. So that is why the solvent is going to interact, and your option will be, correct option will be A, right? CO2 eliminated, AgCl eliminated, and along with that, you are not getting the fluoride to attack over here. You are rather getting the free solvent, which is present in excess, to attack over this bridgehead position. Now, if you want to get a reference of this, because this seems to be a weird question, you can check out in Jerry March as well. Okay. Yes, you can check this out in Jerry March. It's a very nice question. Also, why is the Cl mentioned? Why is the Cl bond into the ring? Because it is not mentioned that whether it is going to attack from the para position or from the ortho or the meta position. All of these position could be anything, or it could be a mix also. That is why the Cl is into the ring, which means there is a Cl substituent without any specific mention. Okay. Next question is super important, TIFR 2017. That is, predict the major product of the following hydroboration reaction. CH3, CH, double bond, another CH3 and another CH3. So this basically is an easy question, that is your hydroboration. Now the R group is bulky, we get that, okay, no problem. Now this could have been a very simple question if there was not heat. But there is heat. Hydroboration is an easy reaction. It does not require heat. But here it's given heat, which means some kind of isomerization of alkene could take place. Okay. So what we can expect from here is a usual reaction would have been like this. Okay. This would have been a usual reaction, that on the least hindered side you are going to get the um, yes, on the more substituted carbon you will get the hydrogen, on the less substituted you are going to get the Br2 group. But the R groups are so bulky that they don't even want to form this. Rather, what will happen in the presence of heat, when the molecule comes in contact, there could be a hydrogen transfer to give you alkene isomerization, right? And here the molecule could add. Okay, so CH2 Br2. This is what you can get. Option number C is your correct answer. Hydroboration does not require heat, and when there is heat and a bulky molecule like this, then you are going to think of isomerization of alkene. This is your correct answer. Okay, not option number B or any other option. Next question, right from TIFR 2017, is very simple and a very good question. what are X and Y in the following reaction? So as you can see, there's this molecule and CSF. Cesium fluoride is an ionic compound. It's a fluoride source over here. Whenever you see a fluoride source, you must think of silicon being a leaving group because fluoride will quickly attack the silicon. But if the silicon leaves, do you also have a leaving group on the other side? Yes, this is your triplet. Yes, isn't it? Trifluoromethyl sulfonate. This is your triplet. This is a good leaving group. So just by a fluoride source, and this molecule is going to form a benzene like this. Now once the benzene is formed, X is your benzene. Okay, so once the benzene is formed, it is going to simply react with furan in this way. You have also got this question in CSIR NET and GATE, both of the examinations, that the furan is a very nice diene compound, and benzene is a very good dienophile. So it is going to give you a Diels-Alder reaction, 4 plus 2 cycloaddition. Sorry, this is a carbon, and the product is going to be like this, a tricyclic compound. This is your option number Y. It can never be trans. This is never possible. Okay, so X is your benzene and Y is your product like this. Now, basically, option number A and D are looking really absurd, and yes, they're not going to happen. What about option number B? You can write the benzene like this also. It's not a problem if you write benzene like this. Okay, in this way, that's not wrong. Okay, but what is the problem? The problem is it is showing you that this carbon of the benzene has not reacted, and only one carbon of the benzene has reacted to give you this molecule. So this is not possible, right? Both of these carbons are going to react with the furan to give you this compound. Okay, so that is why B has to be written wrong. C is your correct representation. So this is a benzene formation followed by 4 plus 2 cycloaddition. Okay. Next question from TIFR 2018 is super good and super easy. Phosphite esters undergo nucleophilic substitution with alkyl halides. Predict the stable product of the following reaction. Okay, you might get confused looking at this combination, but if you know this reaction, you'll do it in 1 minute, right? And I'll just uh, uh, you know send the link, paste the link somewhere over here. We have done this reaction already. Michaelis arbuzo phosphonate ester synthesis. So what is happening? Phosphite ester with alkyl halides, it's going to react in this way. I minus leaves. What have you got? Let's say I'm writing two of the phosphites like this, and one of them in this way. Okay, so there will be a positive charge on phosphorus and an I minus is free. So the I minus will now attack on one of the phosphite carbons so that the bond falls up to phosphorus, and hence you get isopropyl iodide, followed by, there's a double bond with the phosphorus. Two of these phosphite groups are as it is, and obviously the benzyl group is connected. So this is your new phosphonate ester synthesis that you can use for further Wittig reaction from here, but that is not asked. Only the Arbuzov reaction is asked. So B is your correct answer for this question. Next is another good question from TIFR 2020. Now, guys, I am providing you the answers and explanations to so many good questions, and what I ask in return is your support from all of you. And if you are liking the content, if you think that you can clear your exam by studying all of these things, then please share this with your friends as well, and please also show some support to the channel. All right, guys. So the question is predict the product of the following reaction. Now, this is again a very nice question and a tricky one over here. Why? Because you might get confused into how the cyclization is happening if you don't know what this reagent is going to do. Now, this is a very strong reagent, the amide. It can remove protons. How many protons it will remove? Let's see. First proton to be removed is the most acidic one from the nitrogen. Second proton to be removed is right from here. This is also acidic because this is in between two carbonyls. Third proton to be removed is from here, which can give you a benzene. So the overall molecule after the proton removal is going to be like this. This is a CH3 over here, okay? So this is your overall molecule which will be after the proton removal. Now let me also arrange in it a proper manner. Yes, this is what you have, right? Now it will become very obvious for all of you that who attacks who, because this O minus, this carbon has the carbo anion, or basically the enolate has formed last, and it gives you a 5-membered ring for cyclization. So you're going to get a negative charge over here, the nitrogen, new bond, and a ketone group. This is what you have. All right. And since there is going to be ammonia, ammonia is going to quench the negative charges by providing them protons. So the molecule should actually, after gaining protons, the molecule should look like this: NH, the carbonyl group, and the ketone group. This is what you have. But once again, there is the strong base amide. So the strong base amide is looking for an acidic proton, which is right over here. Another acidic proton in between two of these carbonyls. So the final product is going to be like this. Option number B. Alright, so I hope this makes sense to all of you that why did this happen? Because you're having a very, very strong base, okay, and you're having three types of acidic proton, you can result into a benzene formation, okay, right over here, and the attack by the enolate carbon. Next question is from TIFR 2021. Now the question is very simple. The addition of HCl to 1-butene and to 2-butene gives the same product. The rate of 1-butene reaction is faster due to. Now this is such an easy question that sometimes we are not even able to answer, right? Because we are not able to answer very easy questions sometimes. 1, 2, 3, 4. This is your 1-butene and this is your 2-butene. Okay. So it is saying that chalo theek hai, that you are adding HCl over here. So HCl ko if you're adding in this molecule, it's going to give you this kind of an intermediate. And if you're adding the HCl over here, let's say you've added the hydrogen this side, you got the same intermediate, isn't it? And now they are going to be attacked by Cl to basically give you the same product. There is your Cl. Okay, even if you are, let's say, adding the hydrogen over here and the Cl over here, it will be the same molecule. You can just rotate and see. So this is the same product. Why is it the same product? Because the intermediate is same when you're starting from 1-butene or 2-butene. So if we want to draw an energy profile diagram, let's say, of this reaction, let's say this is your 1-butene compound. Okay, and it is forming this intermediate, let's say, and it has to go through an activation energy. All right, Now this is your 2-butene molecule. All right. Now it is also giving you the same intermediate, that is a secondary carbocation. All right, but what happens is, let's say, even if you are keeping the all right, even if you are having the same intermediate, what will happen, guys? On going from 1 butene to the intermediate, you require less amount of activation energy, okay, as compared to in going from 2 butene to the same intermediate. Why is that so? Why is the activation energy higher in the second case? Because the 2-butene molecule is thermodynamically more stable. It's a more substituted alkene system. However, the 1-butene is thermodynamically less stable, so it is already there in higher energy, so easier reaction. So your option is B. 1-butene is energetically higher than 2-butene, and that is why crossing the energy barrier is easy for 1-butene. Okay? So that is your correct answer. 2-butene is energetically lower, it should be. Nucleophilic attack of Cl- is hindered, not at all. Formation of a more stable carbocation by 1-butene, not at all. The carbocation is the same. Since we are having the same intermediate, we can compare the energy of these two. Alright, so this is a very, very nice and basic question that has been asked in very recent year. Now guys, also if you want, I have already shared a lot of important topics on YouTube, and if you also want to study detailed courses about inorganic and organic, that is what I'm taking on Unacademy Plus. Okay, so for CSIR NET or GATE preparation, you can join me on Unacademy Plus by using the code Jagriti S. That gives you a 10% discount in the subscription. Okay, and yes, I hope that those courses are going to be really important if you join, and really, really beneficial to all of you. I'm going to see you in the next such videos. Thank you so much. Have a nice day.